Alrighty, I think we are good to go. Let's make sure I'm recording. I am recording. Good to go. All right, so it is April 20th, 2022. Hello, everyone. I'm going to go over libembeddedhal updates for this last 2 weeks. So, new update, the micromod is in, has arrived, haven't tested it yet, just haven't had the time to. Have been in a lab where I could actually solder the thing together and test it out. But honestly, I'm more focused on some career change stuff, as well as also getting some things in for libembeddedhal. So we're just focusing on that. Some of the highlights, another area that we're going to have on the agenda is the units library decision. I'm certain we're going to go with MP units now. I've been back and forth on this last week, but I'll go into more detail. New policy for floats. Again, I keep having this back and forth when it comes to when are we going to use floats? Won't we use floats? I think eventually I'll settle down on a definitive answer. But as it stands right now, we have a newer policy when it comes to floats. And then progress report for iteration 1. So from April 6th to April 19th. So we'll go over all the things that have been done then, and yeah, I'll show you guys how things are looking on the GitHub organization projects. So let's take a little dive in. First off, we have units library decisions, MP units. So why use units libraries in general? So this is actually a back and forth. I actually was somewhat considering maybe eliminating the units to some extent. I knew some students were having some problems with it, and I was thinking maybe units are a little too complicated, pulling all that library code in. But I also realized that it caused a whole variety of problems on that side. So pretty much the reason why we're using units library is because it's the same reason why we used chrono for time. It handles upscaling and sometimes downscaling values and also conversions. For example, if you pass 1 minute into a function that requires, seconds, it'll do the conversion for you. It won't allow you to do the conversion from minutes to years because that would be truncation, and you may lose information. It may become 0 years because it's pretty much 0 years integer-wise. But scaling down the other direction works perfectly fine. It allows something to take a specific type of unit and have other people put in different types of units, input into it, and just have it all be converted for you, and that's really good. Can help prevent mistakes, as well as makes it easier to see and correct. Them. So when you are writing your code, and let's say you meant to put down 1 second versus 1 minute, or 1 millisecond versus 1 minute, you might have just put one min for minute, and then hadn't really realized what you had done. And you might see okay, something's wrong with my code. Whereas if you do 1 millisecond, let's say you meant to do 1 millisecond, you can go, oh, okay, I see my code. I put min. It should have been ms, not min. Okay, let's replace that. The thing is, if you didn't have any units or any way to kind of declare certain objects as being certain types, you would put 1 there, and you may not know what that 1 means. Maybe you did mean 1 minute, but that means you would have needed to put for 1 millisecond 60,000. If you meant to put 1 millisecond, or 1 minute, or basically vice versa, you run into problems. You have to put decimal 0.0001 to really mean what you wanted, or it's actually not exactly 1, but you get what I mean. Basically, you run into problems with unit conversions, or not knowing what units the thing's supposed to be and putting in the wrong units, and then trying to figure out where the unit mistake happens can be quite complicated. Which is why having a system that literally gives you a compiler error when you make these type of mistakes is best. Yeah, and that's the second part right there, the third bullet right there. Next part is performance. If you want to know about the performance and how it works, you can look at this video here. It goes into detail. It's fantastic. I say give it a shot. It actually is what kind of pushed me over the edge to go with MP units. And there's also a paper, which is a current proposal for C++ 26. So, what will unit libraries be used for? Well, specifically for interfaces. It can also be used for arithmetic and other things like that. Actually, it should be encouraged to be used for arithmetic and stuff like that. But the one thing that we need for libembeddedhal specifically is that we need to have units used for things like temperature, accelerometer, gyroscope, rotary encoder, that kind of stuff. It's important to make sure we have a good representation or a strong type for these type of things. Because if you just use double or float everywhere, you run into the same problem I was talking about before, where you have to document somewhere in your code what type of thing this is returning. I don't think it takes very much for a user to assume, oh, it's millikelvin, right? Versus, or let's say it's for length. Oh, you're using millimeters, right? Versus nanometers. Then do everything incorrectly, and then people's code get completely out of whack. Whereas if you had used units, like a strongly typed library for units, you could kind of mess that up and it would all work out anyway. Because if you're just trying to use millimeters and trying to send that out, then it'll be converted for you. And finally, will this require floats? Because a lot of the times when you do conversions, it requires a lot of multiply and division, and that can cause a whole variety of issues. And that's what we're going to talk about in the next slide. So a new policy for floats again. So floats are allowed within implementations, but discouraged if it can be helped. So that's the new policy. And actually the policy at the bottom kind of explains a little more detail, but basically the policy is that yes, you can use floats inside your implementations. But if you can get away with not using them, you should not use them. Libraries that use floats must document where floats are used. This is actually a part of AutoSAR, which is that anytime you do any sort of arithmetic, you need to have bound checks for each one of those bits of arithmetic. Especially, and you also need to document how it's working, and possibly, if you don't do a bounds check, why you believe that a bounds check is not required. For example, if you multiply two 32-bit numbers, if you have two 32-bit numbers, and then you cast them or set them equal to some 64-bit number, and then you multiply those two 64-bit numbers together, that number will never overflow, because the maximum value for a 32-bit number multiplied by another maximum number, 32-bit number, together will not exceed 64 bits. It'll be actually slightly less than the maximum required to fill that. This is important because then you can kind of get away with not having to do a whole bunch of comparisons when we're in situations in which you know that the arithmetic will never overflow. But if it may, then you need to put checks. That's just a thing. That goes regardless if it's integers or floats. But one of the things that they specify in AutoSAR is that you need to document how you're using your floats and why you believe that it will not overflow or have any of the other weird issues with floats, such as not a number, infinities, undefined, that kind of stuff. Interfaces must never use floats, that includes doubles, for their input parameters or output parameters. This policy is the same for heap allocating standard libraries, and this is to prevent them from being forced into being linked into the code. I need to rewrite this so it doesn't make this is a little less confusing. Basically, let's say we have a parameter like standard string. Standard string, once you have it as an interface, as part of a virtual interface, the code has to pull in malloc, has to pull in the entirety of all the functions for string, or at least all the ones that you're going to use. But a good portion of stuff required for string, like constructing the string, need to be brought in. Why? Because the compiler with virtual functions, like we said before, does not know what functions will or not be actually used in the code. And even if they aren't being used in the code, it cannot remove those implementations off the bat because it doesn't know if there's going to be an implementation that gets loaded dynamically sometime in the future at runtime. So because of that, it needs to pull in all the facilities in order to build up that particular object. So same thing happens with floats. If you have a float as a virtual parameter as for input or output, you need to have at least some basic floating point. For systems that have instructions for it, that's not a big deal. But for systems that don't have it, you need to bring in a lot of floating point ABI stuff into your code. It shouldn't be too much, though. It should just be the some basics for loading or converting between doubles and floats and integers and floats, stuff like that. But that's just something you have to keep in mind. And then currently, subject to change, but if an implementation needs decimal support, it is preferred to use floats when possible and to avoid double unless necessary. Fixed point libraries at this point, which is subject to change, are to be avoided as having libraries that use floats and also fixed point will simply just add more code bloat. We already get 4K or around 2K if we bring in floats. We add in around about 4K if we add floats and doubles and all the other stuff that goes along with it. And then on top of this too, if we use fixed point arithmetic, now you're adding in a whole variety of additional code to the code base. And if let's say you have 5 libraries and all of them use their own different version of a fixed point arithmetic, and you have one that uses float, you now have 5 different libraries doing basically the same type of work. So right now, floats are going to be kind of number one. Oh, and I think I specify it here. I don't specify it here, but it's in the next slide. It goes into which floats you should use and prioritize. So So again, new policy. So integers come in. Your implementation can use floats to kind of calculate what it needs to calculate, and then needs to make sure that it can spit out integers. So integers go in, integers goes out. This is helpful because let's say you have a whole bunch of implementations that just use integers. Well, you don't pay the cost of using integers. If you had to pass in through floats, you have to pay some cost of the conversion from whatever integers you may have to a float. If it's already a float, then there's no conversion. That's fine. But if it returns back an integer or returns back a float, you may have to convert it back into integers in order to actually use, and then you're still paying that cost. So in order to minimize the cost as much as possible, the idea is to have integers go in and integers come out. Also, it's a good policy for the rest of the code so that you never have this expectation that the code doesn't need to be aware of how the implementation is done, whether it's floats or not. It's just to know that, oh, I'm getting back a certain number that I can then use for something else. So that's kind of how this thing should work in general. And finally, with the priority when it comes to numeric representations. Number one, integer math. I should probably say numeric representations. I should probably say numeric mathematics. But basically, integer is number one. Number two is 32-bit floating point math. After that is 64-bit floating point math. And then lastly is fixed point math. Now, 32-bit math brings in around about, I think for almost all cases like comparisons and multiplication, addition, stuff like that, only brings in around about 2K for systems that do not have FPUs, floating point units. I think I have to look at the old numbers. It might even be slightly less, like 17K. You mostly pay a lot of the cost when you bring in doubles. But yeah, so using floats aren't the worst, but we need to make sure we stick with using 32 bits only and not trying to promote up to 64-bit doubles, or just doubles. Yeah. So yeah, this is the kind of hierarchy. And I think, yeah. So how do we support integer units in general? So if we're allowing floats for implementation, but only integers for interfaces, how's it supposed to work? Well, here's our strategy. Here's a strategy I kind of came up with. I think I was talking to one of our members. Yeah, actually, I think I was talking through with someone else, and I kind of came up with this idea as I was talking it through. So find an SI unit representation that fits within a int64 type that fits reasonably for almost all use cases and all applications. So I actually realized that we already do this already. We use the unit nanoseconds. That is our smallest resolution value or unit of time. We don't go any less than that. We don't go into picoseconds. We don't go into femtoseconds. We just stick with nanoseconds. Maybe in the future we will have an interface for high accuracy time or high accuracy whatever that does that. But for now, we use nanoseconds. Chrono nanoseconds uses int64 type. So for 1 nanosecond, honestly, most projects that I've worked with, I've always done things in the span of, well, a lot of times it's in milliseconds for basic things. When you want to look at for performance, you look at microseconds usually. Nanoseconds gives you a lot more space so that you can have things like 523.52 microseconds, or that number, but in nanoseconds. Move the decimal point over. So nanoseconds gives you a lot of resolution for what you need. And it's fine enough for most applications, but also when you look at the scale, how big can it get? Because if you're only using nanoseconds, it may not be a big enough, int64 may not be big enough to hold a large time number. So if you want to, let's say, have a timer run for an entire year before it executes, well, maybe nanoseconds doesn't work for you. Well, no, it does. 2 to the 64 nanoseconds, 2 to 64 is a massive number. Nanoseconds of that gets you around about 292.3 years. I'm going to go out on a limb that pretty much fits most applications. I don't think we're going to have, projects that, well, we may, but projects that will span nearly 3 times a human's lifespan. So I think that's a good enough maximum value. So really what this comes down to is what's the smallest resolution that you need, and then what's the biggest number you can get. Here's another example, nanokelvin. This will be for temperature. Why Kelvin? Well, it's better than Celsius because it starts at 0, so it's kind of unsigned in a way. But we'll still have signed temperatures because we want to be able to create temperature deltas. But Nanokelvin's small enough because it's very, very close to absolute zero. I believe I saw on Google it said like the lowest temperature we ever had. That might have been 1980s though. Was 150 nanokelvin. I think it might be smaller now, but we've been able to get really close to absolute zero. And I think 1 nanokelvin fits most applications that people are going to be doing stuff with, including some scientific applications as well. And then 2 to 63 nanokelvin is about 9.2 billion Celsius. Note that the center of our sun is 15 million Celsius, and a nuclear reactor is up to 100. Nuclear fusion reactor. So we should be able to easily cover all that, like, from cosmology to nuclear reactors to particle physics. This should pretty much fit it. So nanokelvin should work for everything we need. This part here I'm still kind of deciding on, but using femtofarads for capacitance. Why not nano? Because I was actually thinking, well, I just use nano everywhere. Well, it doesn't really work for capacitors because I have capacitors that are less than nano. They're like I have capacitors on some chips that I have that are 12.2 picofarads as load resistors for crystals. So having pico is kind of required, but then, like as I said, I had not 12.5 picofarads. So pico's not small enough either because I need to be able to represent that decimal point. So I went with femto, which is one step below. Should be one step below. I believe it's one step below. I could be wrong. I'm pretty sure it's underneath pico is femto. So with that, we can represent things like 12.5 picofarads, which is probably like, 1 picofarad is probably the smallest you ever really see, because we don't really build capacitors slower than that, because your board will add the capacitance in that range anyway. So, on the flip side, 2.62 to the 63rd power will get you around about farads. Will get you around about femtofarads. Will get you around about 9,223 farads, which is a lot. Although, honestly, nowadays, that's actually not that big, so I may move this thing back to picofarads. I'm going to bump this up to 9 million just to get this in a better spot, because I could literally buy a whole bunch of Maxwell capacitors, supercapacitors, ultracapacitors, that are about 350 farads, and they fit in my hand. Like, it's not that big. And, like, I could put up enough of these in order to get past this value. So maybe we move that around a little bit, but that's kind of where I'm at right now. Oops, and that's pretty much that. So that's pretty much that for our slideshow here. Now I want to go into progress report on iteration 1. Before we go any further, are there any questions on the decisions for unit testing and how testing for units as well as for floats?
I just had one quick question, and that is there any situation in which we would need to use floats? Because I cannot brainstorm off the top of my head any low-level driver that would need a float or a double.
Yeah, this would be more of a driver for like sensors and that kind of thing. So let's say you have like yeah,
that's what I was thinking. I was just trying to make sure that's accurate.
Yeah, so this is only like this was introduced once we realized, all right, we've got the kind of the low-level drivers for basic hardware things. Those will probably never use floats, almost ever. You could consider, what if we need to use floats for like calculating baud rate type things? And not gonna lie, I found a lot of ways to get around using floats in the past, actually just in general. And I think our library for percent can kind of get you where you need to go for the most part. I think also that integer arithmetic can handle it.
Yeah, I definitely agree. Like the only situation which I could see you needing floats is doing some abstract unit conversion that just kind of more helps the user, say like converting Euler angles to quaternions. Because outside of that, you could stay just basic ints and whatever.
Yeah, totally agree. And then like when it comes to like, and here's the thing I bring up too is like, let's say we have a temperature sensor, and it has some sort of like for every volt, for every like volts. Well, let's say it's like for every millivolt, it equates to something Celsius, right? A lot of people would go, okay, well, 1 millivolt over like 0.0001 over whatever that number is, and get that number as like their conversion value, and then multiply that by whatever voltage they get in order to get their Celsius, right? But the thing is, you can just transform your voltage value into millivolts, transform your Celsius value into something that fits in that whatever that denominator is for like what the voltage is compared to the Celsius, and then from there, kind of just multiply things together, like or you do multiplication and division from there. So I actually firmly believe that a lot of this can actually be handled with just integer mathematics. Um, but I do hold that there may be situations in which people need to use floats, and I'll say that the option of not using floats would actually be either a well, yeah, it may be less performant and actually use up more memory than using the floats in the first place. But that just means that they still need to document onto their code that they're using floats and where they're using where exactly they're using floats. And actually, did I put a note about that? I guess when I put a note about this, oh, I did not. I didn't put a note here. I meant to put a note here saying that oh yeah, on the second bullet point, libraries that use floats must document where floats are used, just so that the user knows, okay, when I call these functions or when I use this interface or use this particular library, I'm paying for floats. If I want to not pay for floats, I have to basically eliminate that library. So yeah, any other questions? Good question.
What are your thoughts on using the unit selector as like parameters return type?
Sorry, you're a little choppy there. Can you repeat that?
Sorry, I hit the gym. No, what are your thoughts on like using like a units library for like the return types of like functions and stuff like that?
Yeah. So the game plan here is that if we look at this little example here, I don't have the proper unit here because I'm still trying to figure out this library. It's not gonna lie, it's a little harder to understand than the units library made by Nick Hofhaus. I forget his name honestly, but there's the unit library that we use inside of SJSU Dev 2. That one, we would so that one's a little bit weird. I'm actually not using it for a variety of reasons, but it's mostly because it's not the easiest to basically I want to be able to control the representation. And the way that they allow you to control the representation is through a macro. You can also change it directly by creating your own units in a way, but I also felt that was kind of wonky and weird. And this one looks like it's better slated for better compile time. I actually just checked it. It actually has much better compile time. And it looks like it's slated to be the reference implementation for the standard library. Now, here, going back to your question about return types, here we have virtual MP units. This is made up. Temperature, N64T, something like that, right? This is all made up, at least that part for the return type. But the idea here is we would find out what unit really works for our base units for libembeddedhal, like nanokelvin, and then we would make that the return type would be nanokelvin. And then if you wanted to set something's temperature, like for a house or some type of how should I say this, some sort of heating system, then you'd put your values in nanokelvin. That would be your input. So yeah, so using these units for your output inputs would basically be done as that. And then in your actual interface, the interface for temperature would have a definition for what the standard temperature unit needs to be and go from there so that you don't have to really worry about defining it yourself or trying to remember or anything like that. The temperature sensor will have a defined version for what is the lowest resolution that we support. Sorry, that was kind of confusing. That's all to say that that'll be predefined, and if that library if that interface doesn't already exist, let's say we don't have one for gyroscope, that means the person who writes the gyroscope interface needs to come up with what the appropriate unit for gyroscope needs to be, which is radial velocity, which I don't think exists in the MP units library, which means we may have to use something like hertz, but we'll have to look into that before we start jumping the gun there. But yeah, that's kind of that. Did that answer your question?
Yeah, okay.
Got you. Any other questions? Cool. Alrighty, so let's move over to, let's see what time we have. Okay, it's only about, we've been in here 25 minutes. Let's look over at what we've done for iteration number 1. Iterations like our sprints. I could probably change the name to sprints, but iteration seems fine. It's what GitHub uses, so sure. What is that creaking sound? Oh, it's really windy out here. Okay, so let's get back into this. So let's look at what we have here. So there's a little cleanup on lib ARM Cortex. Moving the boost unit test library into the build requirements, not into the main build. That's to make sure that it only actually pulls in that requirement for builds only, and does not. And if you're trying to install the package, it does not install the unit testing library on top of it because we don't need that for this using the code. So that's the thing. Next up, we have static virtual polymorphism. This actually turned out to be a lot easier than I thought it was going to be. So basically, it works like this, and there's a little demo here. You have some interface, you have some implementation, you create a template, and you default assign the template variable, or template parameter equal to the interface. Then for your actual driver, you can take other types here. So you can basically have a new type for every single variant that could exist. Like there's the temperature sensor, that's the TPM 102, I think. And then you have another temperature sensor like the SI 1070. Well, the constructor will find that specific implementation and will pretty much eliminate all that stuff and just use the interface. But if you wanted to use that specific interface, like that specific type, how should I put this? If you wanted to improve performance, what you would actually do is do this. So let's actually show you a little demo. So in this case, we have user class and we just pass in A into it. In this case, we are using runtime polymorphism. We do not care about trying to increase in performance or changing that kind of thing. We're trying to just use the thing, no problems here. You have a virtual call, that'll happen. It's not that big a deal, not that much. I don't think it's going to create that much of a performance issue, but if it does, then you have the next step here, which is user class, and you supply what the actual name of the implementation is, so the type. When you supply the type here, it now creates a template of that class that knows all the information about that particular interface, so it can actually inline a lot of code for you. I don't know if this code here actually does the best job of inlining stuff for us. Actually does an aggressive amount of inlining, including inlining for this particular class as well. But in bigger implementations, because this is pretty much very dumb one-liners, in bigger implementations, what should happen is that this will do a better job of inlining your code versus this implementation or this use case. But this use case does not use up as much code. For example, you now have a user class template for this one and an implementation for this one. And now you're paying the cost of having two user classes for each type that you wanted to make faster. So either you increase your code usage or you kind of suffer time complexity. But the way you solve it is basically just this way. Make the type equal to interface, make the constructor templated, have it take any arbitrary type, and basically pass it into this. This will throw an exception if you try to throw something in there that does not work. For example, I use like 5 here. Let's make this guy 4. You should give me a compiler error saying that, cannot bind non-const L value reference type reference to a value type. To type int. Does not fit this. It does not initialize, cannot be used as implementation for this T. So that's the thing. Actually, let me get rid of this. It'll just show you that the interface doesn't work. But yeah, that's kind of how that goes. So that's kind of how we do static polymorphism. I hope to do a little bit of write-up later on. This issue will kind of be my write-up for now, so people can use it. It'll have a little, in the guide for how to build drivers, there will be information about how to do this. And I think most drivers that take interfaces will have, and it will be templated and will have their own set of, whole list of, I would call them concepts. They'd have their own templates for each and every type of thing that they could support, and then go from there. And then users can choose if they want to be specific about a particular type or if they don't want to. That's how we handle static virtual polymorphism. And it was actually a lot simpler than I thought it would be. So that's one thing. If you have any questions about this or are kind of confused, just talk and state your question. No need to wait for me to ask you. This is a frequency count update. This brought in quite a few things into frequency count, which we may end up eliminating just because we are probably bringing in a library that can do frequency. Just a variety of things I brought into this, like using, making the actual frequency code safe to use, safe to use, meaning that it won't overflow when you use any of the libraries. It will return errors if it ever detects an overflow. We also added in a multiply with overflow detection. I might actually just truncate that down just to multiply, because it'll just be implicit that it has overflow detection because it can return an error. Make all methods frequency class safe, more safe stuff. only take nanoseconds for a lot of things, and a couple of things here and there. And then also bringing in the wide integer. So if you ever need to, like, if you're ever working with like 64-bit numbers and you need like a pretty bigger number, you can bring in uint 128 and like 256 if you need them. But obviously these will be less performant than just simply using lower width variables. But if you need it for overflow protection, then you need it. So there's no getting around that. So that was cool. We actually closed this particular bug. This was closed because it didn't make actually any sense. So this guy here, this person, I shouldn't say guy, I don't know their gender. But yeah, this person here found us online and said, hey, this looks like a cool project. I want to help out with it. So they're helping with it, and they assigned themselves to this project and made implementation. Then we talked about it a little bit more. It's in the bug information. It's in the issue. Look at it. We just remember to say this isn't making sense. We're going to close it. So that. But this person's also making strides to fix up other things. So that's kind of cool. I do need to tell them though that I need them to back off on some of the easier projects so I can make sure that those are available for other people who are coming into as a starter. Looking at time. Okay. So let's look at mock PWM. Yes, let's look at the PR for it.
I just want to make a quick comment that I'm glad you did one of the mocks, because one of my questions today would have been what your expectations are for one of the mock projects.
Yeah, good. Yep, I'm about to answer that right now. So here, unit tests are required. We add some unit tests. This is a little thing I added into percent, so you can actually compare it in unit tests. Probably gonna keep the percent class unless the units library has their own. A comparison for the configuration. That's a little update here. But now we have the mock. So here's the thing about mocks. They're not like stubs. Stubs are there to do nothing and just to consume information and just to kind of fill a blank, fill a spot. Mocks can either be spies, spy meaning that the library basically just records information about how it was called, or it can actually kind of simulate an actual port. So in this PWM, because all of its return types are void and basically errors, you don't really need anything special from this thing. All you really need to do is spy on it, be able to spy on like all the functions. So in this case, we have a driver configure and a driver duty cycle. And I actually made this thing called a spy handler. So you basically give it what the return type needs to be, what the inputs need to be, and it will do the job of basically returning, like recording the information and then returning either a success error message or an actual error. So it only does two things: either returns an error or it always records what you give it, but it can also return an error. So the spy handler is only meant for boost leap result void. It isn't meant for anything else. I may extend it to handle more things if it makes more sense to handle more things, but for now I just wanted to handle void returns. So here, this is pretty much the entire implementation. We just record what is here and then we return it. Note that if you look at this thing, it's not a class, it's a struct. This is to keep everything here public and only keep a few things private. The spy configure and the spy for duty cycle are publicly available so people can inspect it directly. You can modify it as you like. It's only meant to be used for unit tests. So that's kind of the expectation here. In this case, we only want to know is like how was configure called? Was it called correctly, and was duty cycle called correctly? That's what we're doing here. And if you're wondering why we're not using Fake It or other libraries like that, it's because Fake It takes way too long to compile, and this is snappy. So we're going with this method, and hopefully we can keep spy handle and other mocks as small as possible so that they, as quickly compilable as possible so that they don't themselves also become the same issue. This is a testing library this is a library for handling all the testing stuff. So all of our like spy handler type things will be in here. Mock test pretty much goes over actually testing out configure and making sure that it operates as expected. Have a couple things to expect. We create the mock. We tell it to trigger an error on call 3. So first one, we should basically get the result and it should be fine. We should expect that the in mock.spyconfigure.callHistory, at, and this is a vector, this returns back a vector, at 0, it should be expected 1. When you call it again with this one, the second call, which is at index 1, should be expected 2. And then for this last one, where we call expected 2 again, should actually fail. If you do the not operator on it, it'll convert it into a bool, so it'll tell you if there's actually an error there. And we should be able to get that next element, and it should be at 2, and it should be expected 2. I could have put expected 3 here, and then you would have seen like it would have been expected 3, but yeah, I think I did do that at one point, but thought it wasn't necessary. And then so on and so forth for duty cycle here. The reason why we're casting these things, we're taking these things and putting them into a bool is because the error type needs to be converted either implicitly or explicitly into a bool for it to work. And then next up, we have the tests for the spy handlers. You can see how it's used here. You can look at how, like, what the sizes of call histories to see how many times it's been called, that kind of thing. So yeah, and it returns back a tuple. That's why we're doing the whole like stood get thing. Stood get here is to grab the 0th index inside that tuple. And that's pretty much that little change there. Any questions or comments from, any questions or comments on this? Cool, sounds like it's understood. Awesome. We have a stub for timer. We have a stub for timer. Let's look at that real quick. Real basic stuff. Let's go to this PR. Got test here. Here is actually a stub, and I wanted to bring up this one in particular because it actually does something. Specifically, it's not supposed to do too much except for really tell you if you run schedule, it should tell you that it's running. Now, there's nothing actually running in the background, but it makes sense for driver is running to actually return back something, because otherwise you can have libraries that go, okay, if I use this library and I try to schedule something, I may want to ask if it's currently running. If it's not currently running, I may start running driver schedule again and again and again and again and again. And that could be a problem. That could actually deadlock a project. So what we really want is for this thing to really stay out of the way. So if we run schedule, it should return back true that it's running. If you run clear, it should return back false. Nothing more than that. And this is a case where a stub isn't just returning empty or blank information, it's actually doing something. Note that simply making this thing a bool does not actually increase the size of the object. All objects have to have some size, so they usually default to 8 bits. Bool, it will represent 8 bits, so putting this thing here actually means that it's no different than if it was empty. So not really changing the cost here. And then a unit test, which is very basic. So that's that one. And then DAX, same way. Serial stub, very basic. Let's actually go to the PR for it, see if there's anything special in here. Yeah, just driver configure, return nothing. Driver write, return nothing. Bytes available, return 0. And then driver read just basically takes whatever you pass in, it returns you back a span that basically, starts at location 0 and has 0 length. Basically telling you that you did not get any data. Flush returns nothing, just succeeds, returns back success. And yeah, that was pretty much it. I don't think there's anything more that we had to do because none of these have to do anything special. The only one I was kind of weird about was driver available bytes available. I wasn't sure if this thing should actually give out like a 1 so you can actually parse through something. But I think if you had something that had a serial bus that was optional, you're basically only going to check it every so often. You're going to check it every so often. And if there's nothing there, then you move on. Versus the idea that like if you actually do critically need it, you could deadlock yourself by having no data come in. But that's the case where you should not be using a stub. Stubbing out your serial that way doesn't make any sense. So that's that. And make arithmetic save. Is that my PR? I forget. And then, STM has had its library layout fixed up to fit Conan and to fit the new libembeddedhal standard. So that's been cleaned up. So technically people can kind of start digging in here, but there's a lot of stuff that's not fully put together when it comes to libstm32f10x. So just keep that in mind if you try to write some libraries for it. And that's pretty much everything we got done for this week. So I think there's like what? There's 8. Yeah, there's 9, 10. We got 10 things finished. I think I said last time that we needed at least 3 issues fixed per week in order to hit our target of August. and we're already at like 10, so we're in a good spot. And I think with a lot of them are actually pretty easy, so you can probably burn through those ones. I think the ones that are going to take the longest are going to be the actual driver implementations because you actually need hardware and to debug it. But I think we can burn through a lot of these before we get there. And people who want to jump in there already can go and jump in there if they like. So, yeah, that's pretty much that. Any questions, comments, or concerns that you guys see here? Okay, cool. All right, so that's pretty much the updates for this week, or for like this iteration. I'm gonna start labeling a lot of these projects as iteration 2. So if you pick up an assignment and you get if I feel A, you can get it done in this iteration, or B, you want to slate it for this iteration, or C, it gets finished during this iteration, I will mark it as this iteration. So each time we go back here, we can actually sort by, well, I'm actually going to make a new view. Let me save changes here. And what I want to do is, can I make a new, let's see if I can make a new view off this. Group by view, yeah. So I can actually group everything by iterations here. So okay, let's look at everything that's done in iteration 1. And we can look at everything that's done in iteration 2 and all things that are not currently slated for an iteration. So that's what I'm a little excited about, and hopefully we can get that there. This person's working on stub SPI, and then I'm still working on the proposal for what units should be handled. I want to finish this by this iteration. I'm actually going to put this person's stuff on iteration 2 because this person already has. This should. Wait, when is iteration 2? No, this should be for iteration 3. We'll put this on iteration 3. Yeah, Liz did not start working on this thing until next month, so that shouldn't be there. And then I'm gonna put a couple things here, iteration 2, and then for the rest of the people, I'll let you guys handle when you guys want to do this. I'm not gonna dictate that too much, but yeah. So that's pretty much that. Thank you guys for coming along. I can't wait I hope to see you guys next week, and I hope you guys keep making. I hope we keep making good progress on stuff, and excited to see what we build up next up. So yeah, that's pretty much it.
Quick question.
Yeah,
You
go
said
for it.
next week, or did you mean the week after?
I meant the week after. Every 2 weeks.
Okay.
Yeah, every iteration is every 2 weeks. Yeah, every sprint or iteration is every 2 weeks. Any other questions before we wrap up? Awesome. All right, you guys have a great day today. Be safe, and yeah, see you guys in 2 weeks.